So our next speaker is Professor Feng Wang, again from University of California, Berkeley, and he'll be talking about Moiré excitons in TMD heterostructures.
Okay, this afternoon I will tell more about optical spectrum.
Really?
Interference? I don't know.
Try this one.
Okay, good. So I will talk more about optical spectroscopy to study the van der Waals heterostructures, which is another topic quite dear to my heart. So as I mentioned, there have been a lot of interest in exploring different kind of van der Waals heterostructures, and in the morning I talked about the graphene on boron nitride system. And in this lecture, I will focus on the transition metal dichalcogenide. So I will give you a little bit more background about the general optical response of these two-dimensional semiconductors and what happens when you lay two different semiconductors together to form a heterostructure. So the 2H phase of transition metal dichalcogenide looks like this. So if you look at side view, you have kind of metal in the middle and the chalcogenide on the two sides. If you look from the top view, it actually looks somewhat like graphene, except the A and B sublattice atom now are different. Or once you break the AB sublattice, you actually create a large gap. So there are kind of four main semiconducting transition metal dichalcogenide, MOS2, MOSE2, WS2, and WSE2. They are quite interesting in the sense the electron, the light and the electron interact actually very strongly in this material. And the other one is basically the value degree of freedom in transition metal dichalcogenide can also be quite interesting, and they can be controlled by optical light. First, if you look at the kind of band gap of this transition metal dichalcogenide, they again lie at K and K prime point, just like graphene. And they have very strong spin orbital interactions. So the spin orbital interaction actually lifted the degeneracy of holes. So as a result, there is a so-called spin valley locking. For example, if you look at the lowest energy hole band, at the K point, spin is pointing up. And at the K prime point, basically spin, or negative K point, spin is pointing down. So even for a monolayer transition metal dichalcogenide, we can measure its optical response quite easily. It turns out the absorption of a monolayer can be as large as 10 to 20%. So that really signifies a very strong light-matter interaction. So that will be very useful for us if we want to use optical light to detect all kinds of effects in this material. And also the fact you see this strong resonant peak is an indication there's very strong excitonity effect in the system. It turns out it is known that for a monolayer transition metal dichalcogenide, when you shine light, you always generate electron and hole together, and they actually form a tightly bound complex known as exciton, and they have a binding energy of about 500 millieV. So that's much larger than a typical semiconductor. Say if you have silicon or gallium arsenide, the exciton binding energy is only a few millieV to 10 millieV. I mentioned there's this value degree of freedom in the sense you have to degenerate gap, one at K point and one at K prime point. Or unlike in graphene, it's usually very hard to get to the K and K prime value separately. In transition metal dichalcogenide, one can actually access this value very conveniently use circular polarized light at visible wavelengths. For example, if you shine, say, left-hand side circular polarized light, you can selectively excite only the K point. And if you use right-hand circular polarized light, you can excite selectively the K prime point. or not only can you excite a specific value, you can also kind of detect whether the exciton is one value or the other through its kind of photoluminescence emission. So by looking at circular polarization of emission, we know where the excitons are. And we can also use kind of below the band gaps circular polarized light even to kind of generate a pseudomagnetic field to manipulate those further. So these are kind of some known facts about monolayer transition metal dichalcogenide. So today I will talk about mostly what happens when you actually put kind of two different transition metal dichalcogenide together. So first I will show you how the band actually line up with each other. They tend to form a so-called type 2 heterostructure and leads to very fast charge transfer process. And then I'll show you like if you or just randomly stack two materials together, usually they are not well aligned, so they form a large twist angle. Even in that case, it can be quite interesting in the heterostructure because with this ultra-fast charge transfer, it actually allows us to engineer the kind of valley lifetime very efficiently, and also making use of that, we can actually generalize and kind of imaging a pure spin current and pure valley current. And then I will also tell you what happens when we actually have small twist angle where the Moiré physics becomes very important. And in that case, we can actually see the Moiré superlattice leads to very strong change in exciton transitions, both when you create an exciton inside of one layer or when you create an exciton where electron and hole sitting in two different layers. Okay, so let's start with basically the band alignment of two transition metal dichalcogenides. Say if I have MOS2 and WS2 together, so it turns out almost any combination behave rather similarly. But these are just first example. So if you look at the band gap, they're actually rather close to each other. One is at 1.9 eV, one is at 2.06 eV. However, they usually have a fairly large band offset because the work function of sulfur and selenide are different, or MO and the W are different. So here I show an illustration of the MOS2 and WS2 kind of a conduction and valence band. So what you can see is basically they have an offset and they form a so-called type 2 heterostructure. And what that means is basically the lowest energy state for electrons sitting in one layer and the lowest energy state for the hole sitting in the other layer. For this type 2 heterostructure, a very natural thing that can happen is a charge transfer process. For example, if you create an electron hole pair in MOS2, you can see that the hole actually would prefer to go to WS2 because that's a lowest energy state. So it naturally leads to very fast charge transfer. And this separation of charge can be very important in device applications. For example, if you want to use it for photodetectors or photovoltaics, you really want to separate the charge. And the important question to ask is like, how efficient are these charge transfer? We know it's energetically favorable, so it will happen sooner or later, but or how fast does it happen? Depend on basically the van der Waals interactions between the layer. So we would like to answer that through experimental means. So how can we measure the kind of charge transfer process? So usually we'll use femtosecond pump probe spectroscopy. And that really benefits from the fact that these 2D semiconductors have very well-defined excitation resonances. So that might means by choosing different laser energy, we can actually selectively pump a specific material or selectively probe a different material. So in this case, we can, for example, choose our pump light specifically at the MOS2 so-called A exciton transition. So what you can see is this transition is actually all below the band gap of WS2. So WS2 doesn't absorb at all. So we know we are inject electron and hole only into MOS2. Then we can actually probe the change in the WS2 response. So you can imagine if we excite MOS2 and the charge did not transfer to WS2, then the WS2 absorption will not be strongly affected. On the other hand, after the whole transfer to WS2, then WS2 absorption will get modified. And by looking at the transient behavior, we know how fast the charge transfer process happens. And here I basically plot the photo-induced change in the absorption spectrum. So basically, induced absorption as a function of probe energy and as a function of pump probe delay. So this is where the pump happens. So we pump only at MOS2 Exciton. And then we actually see very strong feature happens almost immediately at these two energy. And they actually corresponds to WS2 Exciton and B Exciton resonance. So what this tells us is basically the charge transfer happens very, very fast, almost immediately. And by looking at so if we actually do a line cut of this one, we can see basically how fast the signal kind of rise up. So as I mentioned, before charge transfer, the signal is very small. And after charge transfer, the signal should increase very quickly. And then it can decay depending on how the charge relaxes. So basically, the rise time tells us the kind of charge transfer time scale. And you can see over here is actually less than, say, 300 or 400 femtoseconds. And that turns out to be limited by the pulse duration of our laser pulse. So if we do a kind of a convolution or deconvolution to take care of the pulse duration, we obtain a charge transfer rate that's actually less than 50 femtoseconds. Initially, when we saw this, we were kind of surprised. We thought initially this layered material, the interaction can be relatively weak, but this really happens at like sub 100 femtosecond timescale. So that seems basically is saying the charge transfer can happen very, very efficiently. Okay.
Quick question.
Yes.
So is this charge transfer through electron tunneling from one layer to the other layer? Or the dumb question.
Yeah. So it's basically coming from electron or hole jumping from one layer to the other layer.
Are they energy matched? I mean, there's a band offset, right? There's a band offset.
Yes, okay. So when we say there is band offset, but these are conduction and valence bands, so you actually have a continuous states that's available. So electron will be energy, I mean, it can be energy matched, not to the specific K point, but it can be energy matched to another energy point.
But then you have to change the momentum.
Exactly. So we believe that
either a phonon or a defect or something.
Exactly. So we think it's most likely it actually involve emission of an optical phonon and then jump to the other point. And in particular, I mean, emission of optical phonon usually can happen very quickly in tens of femtoseconds because the emitting of a large energy phonon tends to be very efficient. Okay. So it turns out that this ultra-fast charge transfer actually can be quite useful in several aspects. In particular, it allows us actually to engineer this Valley lifetime in the heterostructure, as I will show you. So let's actually come back to this so-called Valley degree of freedom. As I mentioned, you have this kind of a valence band split into two due to spin orbital interaction. The conduction band also gets split into two, although splitting is much smaller. And you can use circular polarized light basically to kind of excite a specific valley. So you can kind of create, detect, or manipulate kind of valley excitons. And when you have a very polarized electron generated by light, you can also see interesting transport property like a valley Hall effect, which is one example of anomalous Hall signal. And if you look at the behavior, people initially think like the Valley degree of freedom will be very well protected because if you think about in order for a hole to go from one valley to the other valley, so first you need a large momentum transfer. And at the same time, you actually need to flip the spin. So it's kind of or doubly forbidden to some extent. So you can imagine that this process will happen very rarely. So the kind of very polarized state can live for a very long time. But soon people found that's actually not quite true, in particular if you have a very polarized exciton. So this is experimental study. So even at 4 Kelvin, you can use circular polarized light to generate a very polarized hole, and then you can monitor it by the kind of the induced Kerr rotation, and you can see it decay quite quickly within a few picoseconds. And then it was realized this actually happens because in an exciton you have electron and hole at the same time. So it turns out for a single hole, it may be difficult to jump to the other valley. But when you have electron and hole, they can actually have a concerted action where the electron and hole jump into the other valley simultaneously, basically through an exchange interaction. And people actually estimate this exchange interaction indeed will be at milli-eV energy scale, and that converts into basically a picosecond time scale. So that basically set an intrinsic limit on how long a very polarized exciton can be. So a few picoseconds, there's very little you can do with it. But on the other hand, it also tells us how to kind of break the limit. So basically, what you want is the electron hole don't talk to each other anymore. They don't form an exciton, and they cannot jump together. So you want to suppress the exchange interaction. And so basically, you want to break up the exciton. There are different ways to do it, but I think the most elegant and nice way to do it in a clean sample is actually make use of this heterostructure. So basically, or you can create a heterostructure and you can encapsulate it in boron nitride, so the sample is of very high quality. And so what happens then is basically if you use circular polarized light, you can create electron hole in a single valley. And way before it can jump to the other valley, which happens in a few picoseconds, the electron hole actually will have a kind of a separation in sub 100 femtoseconds. So basically the electron will directly jump into MOS2. So if the electron and hole now sit in two different layers, the exchange interaction can be very effectively suppressed. So they cannot all jump together to the other valley anymore. So then the hole left here basically can have very long lifetime. Yes?
Could you put the previous slide?
Yes.
So here the valence band has a spin splitting, but the conduction band spin splitting is very small, seems right?
It also has a spin splitting, but it's quite a bit smaller, yes.
So I'm thinking that if the conduction band is also spin split, then the exciton in K valley and in K prime valley, I think is there some selection rule forbidding them to transition from one to the other?
So what happens is basically the electron and the hole, the total spin is actually conserved. So they can go together. So individual.
Right. But the two values, I think they have opposite angular momentum.
They have, but if electron and hole go to, so electron and hole, the total momentum is 0.
You mean including spin and orbital, the total momentum is 0?
Yes.
Okay, we can discuss. Yeah.
Oh, sorry. You're right. So it's actually okay. So the total angular momentum is indeed opposite. So what happens is actually in order for them to go there, you do need a slightly finite momentum. So basically, if it's exactly at the kind of exactly at the decay point, is actually indeed forbidden.
Okay.
But even if you have a very small kind of deviation of momentum, it becomes allowed, and that basically will limit it into kind of a few to 10 picosecond range. Yes. Yeah, that's a very good point. Okay, so before I show you the experimental result, first we would like to actually know, or even if we can create this, if I have only a hole sitting at the K valley, how would I know? So how can we detect it? So again, we'll make use basically a circular kind of a polarized probe, and I want to show you what how does it work first. So imagine like I have a hole, which is shown here, sitting at the K valley, and I actually use a left-hand circular polarized light to actually probe it. That means I will also generate an exciton in the K valley, and we'll see what's the hole effect on that exciton. So what you can see is basically, this hole will form a Pauli blocking effect for this exciton transition to happen. So that means it will suppress this optical transition. So it will reduce the intensity of the absorption. And it turns out when you have a hole sitting with an exciton in the same valley, it also will shift the exciton transition a little bit to blue So this is basically the effect you should see. So once you have basically hole in K valley and probe an exciton in the same valley, you will see reduced exciton strength and a very small blue shift. On the other hand, if you use right circular polarized light, where you actually tend to excite the K prime exciton, the behavior is very different. So first, you can see there is no Pauli blocking, so there is no net oscillator strength change. But what will happen is basically the exciton can still have kind of a Coulomb interaction with the hole in the other valley. They actually can form something known as a trion state. So what that does is basically it will take some oscillator strength from the kind of exciton state and move it to basically the trion absorption. So the total oscillator strength remains the same, but you will see a decrease here and an increase there. And this is indeed what we see experimentally. So here I show you basically after we create a hole in K valley, as I described in the heterostructure, and then we basically probe the kind of K valley exciton absorption. So first, the blue curve shows the pure absorption itself, and then the black curve symbols shows the photo-induced effect. So what you can see is there's a reduction of absorption, so that coming from Pauli blocking effect. And then there is also a small tail due to a very slight blue shift. And the behavior is completely different when you have kind of a right-hand circular polarized probe. In this case, what you can see is there's a reduction in the exciton absorption, and then there's an increase of absorption at lower energy that actually corresponds to increase of trion absorption. And very importantly, if you look at the positive area and the negative area, they largely cancel each other. That basically means there is really no Pauli blocking effect for the basically sigma minus probe. And that means we actually generate holes only in K valley and no holes in K prime valley, because if you do have significant holes in K prime valley, you will also see basically an overall reduction of the oscillator strength. And by analyzing this, we can actually estimate that we create almost a pure valley polarization when you have circular polarized light with the heterostructure within like 5 to 10% experimental uncertainty. And that kind of makes sense because the charge transfer rate, which happens at 50 femtoseconds, is much, much shorter than the exciton depolarization time. So way before exciton can depolarize, everything actually is separated, and then you have a very well-defined valley polarization. And then we can also look at the time dynamics of this valley polarization. So we again measure the circular dichroism signal after the excitation and then do a pump probe measurement. So usually in our optical lab, we do this pump probe measurement with femtosecond light, and we use a laser delay line that usually allow us to scan to several nanoseconds. So compared with femtosecond or picosecond, this is pretty long. So we usually think that will be a long enough decay, and you can see nothing happens. So it certainly lasts much longer than a few nanoseconds. And in order to do longer scan, we actually use electrical delay line. So basically, we use electrically controlled optical pulse. Then we can separate the delay arbitrarily. So what you can see, actually, the decay, now the lifetime is much, much longer than a few picoseconds. It's actually at microsecond time scale. And this is the overall decrease of circular dichroism signal. So if you think about what caused the decrease of circular dichroism signal, there are actually two possibilities. So as I mentioned, we created the kind of a hole in one K valley, and then all the electrons basically go to the, say, WS2 layer. But sooner or later, this electron and hole will still recombine. I mean, or they are separated, but energetically, they still want to recombine. So they still have a recombine lifetime, happens at about 100 nanosecond and 1 microsecond scale. So that basically leads to a population decay. So that also will change the overall circular dichroism signal. So as a result, the circular dichroism signal actually can have two contributions. Basically, one is the overall kind of a population decay, And the other one is actually the kind of valley polarization. So basically the difference between the K and the K prime contribution. So what you can see is that this is a overall circular dichroism signal. It can be written as total hole density, which is related to population decay, and basically valley polarization defined by this. So that actually tells us the inter-valley scattering time. And we can actually measure them separately. So by measuring the sum signal of K and K prime valley and different signal at K and K prime valley, we can basically measure the P plus minus P1 and the P plus plus P1. And you can see they actually decay in a very similar fashion. So the ratio of them tells you the kind of valley polarization, and you can see that actually remains almost constant in many, many picoseconds. So we actually estimate inter-valley scattering lifetime is very long. It's actually more than 40 microseconds. So compared with, say, or Exciton valley lifetime, which is only a few picoseconds, that's an increase of 1 million times. Now with this very long-lived valley polarized holes, we can actually do more things to it, because if they are long-lived, they will move around, so we can actually make use of it in transport studies and manipulate them much more easily. So one thing that we actually tried is to use this very long-lived valley polarized holes to generate some pure spin current and valley current. But before I go there, I want to say, like, as I mentioned, if I have pure charge-neutral heterostructure, the total kind of valley lifetime is limited by the population lifetime. So although the intrinsic inter-valley lifetime is much longer, we cannot use it directly because the population basically is gone. So it turns out there's a nice trick to go around it. And that is, instead of starting from a charge-neutral situation, we actually start with a situation that is initially hole-doped. So as I illustrated here. So initially, it's kind of hole-doped with the red part here. And then if we use circular polarized light, we'll inject electrons in K valley and the hole in the K prime valley. And then within 100 femtoseconds or 50 femtoseconds, the electron will go to the WS2. And then basically, in a later time, the electron in WS2 will recombine with holes in WSE2. But interestingly, because the spin orbital coupling is smaller for electron conduction band, the electron actually randomizes its spin and valley much more easily than holes. And what that happens is basically when it recombines with a kind of a hole, it will recombine with both K and K prime valley holes with almost equal probability. So what happens then is even after the population decay, all the recombination has happened, you are left with a net population difference at the K valley and K prime valley. So the total charge density remains the same, but now you have created a valley imbalance. So more holes in K valley and less holes in K prime valley. And in order to relax this imbalance, so the only thing that can happen is inter-valley scattering. So that can have 10 microsecond lifetime. So now we can actually really access this very long inter-valley lifetime. So experimentally, to realize this kind of things, we make a heterostructure that we can then, with electrostatic gating, so we can control the carrier concentration. So basically, we have this WS2, WSE2 heterostructure encapsulated in boron nitride, and then we actually put a graphene contact that allows us to gate it, and then we use a graphite backgating this device. And here, just to convince you that we can indeed gate and change the carrier concentration in the heterostructure, we show basically the kind of optical absorption spectrum as a function of probe photon energy and as a function of electrostatic gating, so both to the hole side and the electron side. And you can see there are kind of two main features. One corresponds to WSE2 exciton resonance, and the other corresponds to WS2 exciton resonance. So what you can see is, like, if we kind of dope it with holes, this part changes most dramatically, right? So what that says is basically if you dope it with holes, or hole actually would prefer to sit in WSE2 layer. So as a result, you will see basically it modified the exciton transition mainly in the WSE2 layer. So it basically transfer some of the exciton energy, spectrum to the trion, and you see large modulation, but there's very little change in WS2. On the other hand, if we gate it to make it electron dope, then you can see electron prefer sit into the WS2 layer. So, and indeed what you can see is basically WS2 exciton transition gets strongly modified, and very, very little happened for WSE2. Okay, so now we can tune the carrier concentration freely. So we will actually choose a slightly hole doped range. So basically we put some initial hole doping in WSE2. And once you do that, we can see that indeed we can create a whole imbalance that can last for very long. So the lifetime is about 20 microseconds. We can indeed access the intrinsic intervalley scattering lifetime. And with that, then we can actually, as I mentioned, we can generate basically a valley hole imbalance. And since they are locked to spin, we effectively also created a spin imbalance. So we have more spin up holes and less spin down holes. And if we create it locally in a device, so what you can, basically if we just use a kind of a local laser excitation, as I described here, so basically then I will have kind of a net excess of K valley hole here, and a deficient of K prime valley hole here. Basically they want to diffuse around. So the K valley, the actual K valley holes basically wants to diffuse out, and then the K prime valley holes actually want to diffuse in. So what you can see here is basically you actually have net zero, zero charge flow, but you actually have a well-defined valley current flow and spin current flow along that direction. So this basically creates a fairly interesting opportunity that you can actually generate a pure spin and valley current without any electrical field. So just by local circular polarized laser excitation. And in order to probe this valley current, we actually can use, again, spatial and temporally resolved laser spectroscopy. So the idea is basically we can pump locally at one position at a specific time, and then we can probe with another laser that actually is delayed in time, but also we can control their spatial separation. So basically we can really monitor the position of the spin polarized holes as a function of time and space. Or if you have space and time, you know the velocity and you know basically the diffusion process. And this is kind of the experimental data. So we can measure the circular dichroism signal, which basically tells us where the valley polarized holes are. So that's shown in the color as a function of pump probe time delay and pump probe spatial separation. So what you can see is that the zero time, so all the holes kind of sit close to kind of a zero, basically where the laser excitation is. And after kind of hundreds of nanosecond to 1 microsecond, basically they diffuse out. And this indeed agrees quite well with basically a pure kind of a two-dimensional, actually effectively one-dimensional diffusion model, because we excite with a line excitation. And to be more specific, we can actually kind of compare with the theoretical predictions. And you can see if you have a point that's very close to the pump point, you only have a decay that associated with diffusion out, and then a much slower decay due to the intervalley scattering. And if you sit at a position that far away, you can see basically you have diffusion current flow in first, so the intensity increase very quickly, and then decay kind of slowly afterwards. So that allows us basically to determine quite a few important dynamic parameters. For example, we determine a valley kind of lifetime of 20 microseconds and a diffusion constant about 0.2 centimeters squared per second, and the diffusion length about 20 microns. So this actually valley polarized current can actually diffuse quite long, so much larger than a kind of a typical device. And another thing that I would like to point out is actually the diffusion constant is actually related to mobility through kind of a Einstein relation. So that actually tells us, with this pure optical pump probe measurement, we can start to access the kind of a transport property in the material. And this is not quite trivial in this system, because in transition metal dichalcogenide, a very large experimental challenge is actually to make a good contact. So if you don't have good contact, it's very hard to measure kind of transport property and determine the mobility, especially at low temperature and when the carrier concentration is very small. But here, basically, this is a completely contact-free detection. Actually, by purely optical technique, just with like spatially and temporally resolved measurement, you can actually directly determine the propagation of charges and spins in the 2D system, and you can actually use it to extract important transport parameters. And then basically, this just shows we can use like circular polarized light to locally generate a spin current, and we can use another circular polarized light to detect it. And if you calculate, actually the effective Valley current density is actually quite high, and then this is a kind of a pure optical method, so it can be quite complementary for compared with kind of a electrical generation of spin current.
So yeah, sorry.
Yes.
Yeah, I missed the part. So how did you detect it?
Oh, so I mean, it's really by mapping the spatial and the temporal. So what you can see is basically, initially all the spin polarized holes are here, and then basically at a later time it diffuses out. So so if you map density as a function of time and space, then you can calculate what's
This is through the electron hole combination that emit a photon.
Oh, no, sorry. These are all through kind of a pump-induced circular dichroism signal. It's actually all, okay. So basically, so it's still through this scheme. So what you can see is if we actually choose the right probe, so basically we can actually selectively probe how many holes are in the K valley relative to how many holes are in the K prime valley. So basically, the circular dichroism signal, by measuring the reflection change induced by the hole density, we can actually determine the local hole density. That's what it works. Okay, so in the next part, I would like to talk about what happens actually when you go to small twist angle. So in that case, you actually will start to have Moiré superlattice, and their effect can become quite strong. So so basically, when you put the two TMD together, they can form Moiré superlattices. And it actually, Alan McDonald had a theoretical prediction a couple years ago to say basically, once you have this Moiré superlattice, it can not only change electronic band, it will also change the exciton band and change the exciton transitions. So he predicts there will be new peaks actually emerging due to layer-layer interaction. Although he predicts when the angle is relatively large, so larger than 1 degree, the effect will be rather small, and it happens kind of at very low energy. But nevertheless, we want to just see what happens experimentally, so we went ahead and tried to do the experiment. And again, we make use of a hetero bilayer with WS2 and WSE2. So we choose them because it turns out all the sulfur-based TMD and the selenide-based TMD has a relatively large, has a well-defined lattice mismatch. If you are MOS2 and WS2, if they have the same chalcogenide, it turns out that their lattice is almost exactly the same. But if you have different chalcogenide, the lattice match is about 4%, and that's what we like. because we want to form a Moire superlattice that's determined purely by the lattice mismatch. So we don't need any twist angle. So we can just set the twist angle to be 0 or very, very small, so it doesn't matter. So we always have a well-defined Moire superlattice. And for the transition metal dichalcogenide, we also have a very nice way to experimentally determine what the twist angle we have. Because use second harmonic generation, or it turns out for this transition metal dichalcogenide monolayer, it breaks inversion symmetry. So it has well-defined second harmonic generation, and it also has well-defined second harmonic generation patterns as a function of kind of angle. So by looking at where the second harmonic is being generated, we can actually determine the crystal lattice of this sample. So as a result, basically we can determine, for example, in this case, the twist angle is within 0.5 degree for the WS2 and WSE2. And then we actually made the sample and did a transmission electron microscopy to really make sure the Moire superlattice is there. So you can actually clearly see that the periodical pattern is over there. So you do have fairly Moire superlattice. We also noticed that all this, unlike this Moire superlattice, which is exists but kind of more spread out, this Moire superlattice looks like fairly concentrated point. So that's actually an indication there's fairly strong kind of lattice reconstruction in this situation when the two layers interact with each other. So that's a good thing that tells us they are indeed interacting fairly strongly and can have large effect.
Is it strained? The superlattice doesn't look nicely triangular. Or is that just, I'm looking at it.
Yeah, they are reasonably triangle. I think there might be a very small strain. And these are actually TM samples where you basically have heterostructure on top of like a TM grid. So they are suspended and they are more easy to generate like a strain and so on and so forth. Okay. For the device that we used for the optical measurement, they are encapsulated boron nitride and on a flat substrate. So I guess the strain effect will be less. Okay, so let's see what happens to the exciton optical properties. So for a single layer, as I mentioned, there will be well-defined resonances. They are known as A exciton and B exciton. If we have large twist angle, like I have shown previously, the spectrum can be largely described by the sum of monolayer WS2 and monolayer WSE2. So you can see well-defined WSE2 exciton peak and the WS2 exciton peak and so on and so forth. But once you have the Moire superlattice, when the twist angle is small, you can see things change quite a bit. So the spectrum is very different from large twist angle. And the most striking feature is actually at the lowest energy peak. So if I flip here, so you have a single WSE2 A exciton when you have a monolayer or large twist angle. But in the kind of Moire superlattice, it really split into 3 different exciton peaks. And the energy splitting is fairly large. It's actually 60, 70 milli-electron volts. So that means the Moire superlattice are really strongly affect the exciton band structure. And in order to kind of describe what we see experimentally, we try to use some phenomenological model. So basically we say, there's well-defined initial exciton kind of dispersion, and we add an effective potential on the exciton band and see how the band will change and how the exciton transition will evolve. So what we found that we actually need to have a periodical potential V of kind of 25 millieV. So it turns out this is 25 millieV in one of the 6 actually or cosine waves. So this actually corresponds to a potential maximum to minimum of almost 200 millieV. So that's actually a very large Moire potential for the exciton in order to produce kind of changing optical spectra that we see experimentally. So you can see 3 kind of well-defined separated peak with a separation in the order of like 70 millieV. And also, if you look at the kind of exciton wave function, we found that all they tends to be kind of rather localized, and the different exciton transition actually tends to be localized at a different part of the Moire superlattice. So it turns out that the lowest exciton actually sit at this this part of the Moire superlattice, and the second exciton peak is actually localized at a different point. And then the third exciton transition sit again at this point, but it actually has a different type of wave function. So, okay, so that is what we see for the so-called intra-exciton transition. So basically, once you have the Moire superlattice, how does the exciton transition in WSE2 layer change? So where the electron and the hole actually sit in the same layer. It turns out there is another type of exciton that can exist known as interlayer exciton. So which is kind of shown schematic here. As I mentioned, if you excite the electron hole initially, the absorption is actually dominated by the interlayer transition. You create the electron hole in the same layer, but after some time, the electron hole can separate. And then even if they separate into two layers, they still see each other. I mean, they cannot recombine that easily, but the Coulomb interaction is long range, so they can still form a bound exciton state where you have electron on one side and hole on the other side, and this is known as interlayer excitons. You can imagine if electron sitting in one layer and hole sitting in the other layer, this type of interlayer exciton will depend even more strongly on the Moire superlattice or local stacking order of the TMDs. So for example, I again show this Moire superlattice. So within a unit cell of the Moire superlattice, you can kind of think at a different point really corresponds to different stacking order. For example, at this A point, they basically have the so-called AA stacking. So the kind of metal and the chalcogenide align separately with each other. And at this B point, for example, they are more like a AB stacking, as you can see, like a graphene AB stacking type, where you have basically one atom sitting in the middle of the hexagon. So the theory basically predicted a different kind of stacking order will give you different energy landscape. And in particular, there will be kind of a two low energy exciton state, one sitting at the A point and one sit in the B point. So basically you can indeed have kind of a different interlayer excitons sitting at a different part of the Moire superlattice. And there is even more interesting prediction is like all these interlayer excitons sitting at a different part will have a different kind of optical selection rule due to okay, so first let me just have a quick summary on what are the possible low energy exciton states that can exist. So basically they can exist either at the B position or A position. So those are kind of two low energy point. And then for us, one specific stacking order, you can actually potentially have two polarization states. One is electron and hole is actually sitting in this way. It turns out that they have opposite spins. And the other one is basically the electron actually sitting in the second part of the conduction band. So the band-band separation for conduction band is only tens of millieV. So this state also has relatively close energy compared with this ground state. So you can have these two type of states sitting at B point and these two type of states sitting at the A point. So in principle, there will be four kind of interlayer exciton state with relatively close energy. And then there is another very interesting aspect, that is once you have this Moire superlattice, it actually changed the it generated a kind of a new effective quasi-angular momentum depending on the layer-layer stacking, and that will change the optical selection rule in the system. So basically, if you have a threefold rotation symmetry, you can actually define a quasi-angular momentum that basically is 1, 0, 1, 2. And if you look at the A sublattice, so if you look at where basically the atom align very well with each other. And if you consider the top layer and bottom layer separately. So in the top layer, as Liang has mentioned, the wave function sit at the K point. As a result, the atom actually has a so-called winding relative to each other. So basically, the phase at a specific point has 0 and 2 pi over 2 and 4 pi over 2 and so on and so forth. And if you choose the center to be here, you can see there is actually a left-hand winding. So basically, you have an effective quasi-angular momentum of 1. And if you look at the bottom layer, basically the lattice is aligned in the same way. So it also has an angular momentum winding of 1. And the difference between electron and hole will actually be 0. So basically, the excitons basically will not experience a net quasi-angular momentum from the Moire superlattice. However, if you look at the kind of a AB type of stacking, what you can see is basically this lattice is effectively or shifted down by 1 bond. So it's shifted down. So although the phase at different atoms is still the same, but if we choose the same, this point as basically this center point as our reference point, then the effective phase winding actually changes. So you can see now if you choose this one to be center, so 0, 2 pi over 3, 4 pi over 3 is still 1 for the bottom layer. For the top layer, now you can actually see the phase winding looks like this now. So it actually, when you have 0 to 2 pi over 3 to 4 pi over 3, instead of going kind of counterclockwise, it's actually now going clockwise. So basically, it has a net effective angular momentum equal to -1. So that means if you want to combine electron and hole together in this kind of a B stacking order, you actually have a net effective angular momentum change by -2. So indeed, the stacking order actually can give you an emerging angular momentum and determine the selection rule. Okay, so these are all theoretical predictions. So the question is, how do we verify and determine basically the kind of a Moire angular momentum and the spin and the kind of valley state for specific exciton transitions? So for a long time, people we know that this state tends to be the lowest energy, relatively low energy state. So once you create the exciton, they will relax to this state, and they will give rise to photoluminescence, because usually the lowest energy state tends to be the most longest lived state, and the final light emission tends to come from this state. So basically, you can have well-defined photoluminescence coming from this. But usually, only the lowest energy state kind of emit. So it doesn't tell you all the behavior of different exciton state when you have photoluminescence. So what we need is a kind of or more like an absorption spectroscopy. So we can actually see the absorption of different states and how the property of different absorbed state. Experimentally, this is actually quite challenging, because when you have electron and hole sitting in different layers, the absorption becomes much, much weaker for electron and hole sitting in the same layer. It's the oscillator strength is decreased by like 2 orders of magnitude. And in order to measure absorption of this, we use kind of some effectively background-free detection. So for example, one method we use is so-called photoluminescence excitation spectroscopy. So what we do here is actually, we know we can observe photoluminescence, and we will monitor the photoluminescence intensity as a function of excitation photon energy. So basically, if the incident photon energy kind of is absorbed, then you will basically be able to see some photoluminescence intensity. So that actually provides a very sensitive detection of the optical absorption. And the main advantage of this one compared with a direct absorption measurement is background free. Because if you just do a regular photon absorption, the difficulty is not detect your signal is more like the background is too large. You have a transmitted light, and your signal is really overwhelmed. On the other hand, in this case, basically, if you don't have absorption, you don't have any photoluminescence. So basically, so you measure only the net absorption. Another kind of background-free absorption measurement can be done with, again, a pump probe spectroscopy. And in this case, we actually first excite an interlayer exciton. Even if it has very kind of weak absorption cross-section, you can create some of them. And then you use another interlayer exciton as a probe to see the induced change in the kind of interlayer exciton absorption. Again, if you don't have the initial pump absorption, there is no induced change. So the background is zero. And only when you create basically the excitation, you will see an induced signal. So again, this is a background-free measurement. And the advantage of this measurement is basically, since we are probed with an interlayer exciton, we can actually determine, as I mentioned previously, the valley state of this hole in WSE2. So by using circular polarized light, we can actually determine specific valley state of these holes. And combine this together, we actually were able to measure different interlayer exciton state, as well as the spin and the valley and the kind of Moiré angular momentum. So here I basically show you photoluminescence excitation spectroscopy state study first. So we can see photoluminescence at about 1.43 eV, so that is one exciton state. And then basically we can change our excitation energy and monitor the PL intensity. As you can see, the PL intensity is changing when we change the incident energy. And each peak basically corresponds to a resonant interlayer exciton absorption. So basically we determine these two kind of interlayer exciton state. And also by using the kind of pump probe spectroscopy, we can again observe the same like interlayer excitons, basically one at 1.45 and one at 1.51 eV. And we can also see in this case actually 1.43 eV, basically the state that emit photoluminescence actually has very little signal. So that tells us that state is actually a dark state. Okay, so by combining all this together, we can actually really determine the spin and valley state for individual transitions. For example, if we look at this kind of so from pump probe measurement, we know basically the resonant energy, for example, and we know basically it's a strong signal. So basically it will be allowed transition in both spin and the valley. And by looking at the incident circular polarized light, we know the total quasi-angular momentum. And by kind of the induced change in the circular polarization, we can actually know the spin order of the holes or which valley the holes are. So these are the things that we can determine from the experiment. And then basically from that, we can actually also infer basically there is a zero Moiré quasi-angular momentum. And that basically corresponds to AA stacked configuration for this transition. And then we can actually do it for the kind of three different transitions. So we actually found that this transition are coming from like a Moiré position of B, and it has an effective angular momentum of -2. And then the other state is actually coming from A configuration. So this is kind of the summary of what we can determine experimentally. So what you found is basically the kind of opposite to what theoretical prediction is. We actually found that the lowest energy state is not sitting at the A position, but instead actually sitting at the B position. And you basically have a spin forbidden transition that's actually the lowest energy transition. Although it dominates photoluminescence because it's the longest lived, it actually has relatively small oscillator strengths. And then these two are basically allowed transition, and they have like strongest oscillator strengths. And we can indeed verify basically this kind of state have effective quasi-angular momentum, angular momentum coming from the layer stacking order. Okay, so I actually already come to almost the last slide. So I have talked quite a bit about optical transitions and excitons. I feel maybe that's not the topic most of you are most interested in, and then maybe you are wondering, oh, how about electronic bands? How about correlations in this in this Moire superlattice? I don't have too many results, so I have only one suggestion. One slide make some comments. So as I talked in the morning, so this system certainly has fairly large effective mass. So the mass is about 0.5 rest electron mass. And we can create a large enough Moire superlattice. So if you combine this always, you'll get strong correlation. So it is certainly expected. And we can also look at some experimental evidence. So we can actually compare what the kind of Moire exciton bands look like and kind of infer a little bit about how the electron Moire band will look like. As you can see here, this actually, all exciton Moire bands, some of them are really flat. And so if you look at the lowest energy one, so the band dispersion is only, actually the maximum one is about 20 millieV, and this one is actually quite a bit smaller. And I would like to say, the fact that you have two bands here rather than a single band here is, again, due to the exchange interaction in excitons. So it turns out, due to the exchange interaction, the k-value exciton and k-prime value exciton are not completely decoupled. They actually can mix, so that's why you actually have a split of the band. If you don't have that exchange interaction, as if you have, say, a single electron and single hole, that effect will be missing. So then the band will be really flat. So I think the band will likely to have a bandwidth that's less than 10 millieV. So you should have a very kind of flat band that's much smaller than electron Coulomb energy. So it's again should exhibit very strong actually correlation behavior. However, experimental challenge that has plagued us for a long time is how to make an experimental device for transport study. So it turns out for these materials, it's very difficult to form an ohmic contact. So we tend to form resistance that's many gigaohm at low temperature. So that really prevents us to study kind of transporting the Moire superlattice. However, there are ways around. So in order to solve the problem, one of the way to do it is just improve your contact. And that's indeed many transport groups are actually have been perfecting. There have been some preliminary results from Phillips group and the Corridin's group and the Kim-Fai Max group where they actually were able to make reasonable contact. And they actually indeed see indication of multi-insulators at half filling, and Philip even have some kind of data suggesting it could be getting close to superconducting when you dope the multi-insulator. Another approach that we are pursuing more, because it turns out the contact is really difficult for us, we're actually trying more is using optical detection. As I mentioned previously, if you use spatial and temporal resolved optical measurement, you can actually infer the transport property without using any contact. So we are kind of explore different variant of that. So basically use spatially kind of resolved optical probe to directly determine some of the transport properties. And I hope I will be able to tell you more result of that once we move further on these studies. And with that, I would just conclude here. So basically, when you stack two layers together, things can change quite dramatically. Even if you don't control the twist angle, you can actually have ultra-fast charge transfer, and that allow you to have kind of new ways to control the spin and Valley lifetime and the transport of Valley current. And then when you have small twist angle, basically the Moire physics exists, so it actually will affect both exciton transitions as well as electronic transport. And I would like to say a few attractives. If we can get this solved, actually there are several nice advantages of the TMD heterostructures. One is actually, now you can probe the Moire, flat band electrons with more probes, because you actually have very strong optical excitation. You can see how the, say, multi-insulated state can interact with exciton transitions. And the other thing is basically due to the spin-orbital interaction, the optical light actually allow us to generate spin kind of imbalance and also detect how it evolves. So maybe this will actually allow us to study, say, kind of spin dynamics of the multi-insulator regime using kind of optical probe, which will be very difficult to realize in graphene. So, or how to get a hold of spin in graphene is much harder. But with this, you can actually use light to either kind of a control spin state and actually monitor the evolution of the spin state. Okay, so that's it.
So it looks like we have time for questions. Yeah.
I have a question on the pure image pure very current. Do you mind go back to that slide? Yeah.
This one, or you want to see the diffusion?
Yes. Oh yes.
Yeah.
The next slide.
Yeah.
I see the diffusion content is just 0.2. That means the corresponding mobility is roughly 10. That's quite small in TMD heterostructure. So I wonder the material may have some defects or some other disordered effect. So purely the defects or other like disorder effect will generate trapping states or band tail states. I'm wondering in this case whether the trapping states will contribute to this long-lived holes.
Okay, that's a very good question. So the question is like, or the effective mobility coming from this is actually quite low. So why is it? I mean, is it due to defects? Okay, so the answer is like, indeed, if we convert this into kind of a mobility, it's only in the order of like 10,
Yeah.
tens of. But we actually found that the mobility actually changed quite a bit with the doping.
Okay.
So if we dope it a little bit more, it can be higher. So it can reach more like 100. And this is actually quite, so that part indeed, I think is partly defect related. So if you have low doping, you are close to the mobility gap, then the mobility indeed will be lower. So the best mobility in TMD people usually observe is indeed in highly doped sample. On the other hand, I do feel like this long-lived spin are not because of purely localized state, because if they are purely localized, you would not, okay, so they might stay in defect a little bit, but overall they certainly can propagate. So they are still moving, they have well-defined transport properties.
Yeah, I just missed this part. You already described how this is detected. You also said how this is generated. I missed that part.
The generation is very simple. You just excite at only a single spot. So basically here, you just use a circular polarized light over here to shine on this spot. So basically at this local spot, you will have actual kind of K value holes and the deficiency of K prime value holes.
These are real excitations that
use real excitation, yeah.
So what about then the electrons?
Oh, okay.
You excite both electron holes, right?
Yes. So this is actually what happens overall. So you actually create electron holes at the same time, and then electrons goes to WS2, and within 10 to 100 nanoseconds, the electron actually will recombine with holes. So the electrons are gone, and you are actually left with a net, basically, redistribution of holes. So this is basically what we have after, say, 10 to 100 nanoseconds locally. And this pure kind of whole population, polarized whole population can diffuse.
After a few tens of nanoseconds, there's no net charge density, but there's a net valley polarization.
Exactly.
Okay. Very interesting.
One more question, yeah.
In one of the last slides where you showed the band structure of excitons, the energy scale was in electron volts?
Milli-electron volts.
Milli-electron volts.
Yes.
Okay. Another question is then, are there any interaction effects between the excitons observed, like when you increase the pump pulse, something non-linear, blue shifts?
Yeah, that's a very interesting question. Like if we pump it, certainly the spectrum is evolving if we pump it very strongly. We haven't looked at it systematically. One thing is like we try to avoid like a too strong pump because that has a potential to damage the sample. So we try to kind of working mostly at the low fluence limit. But it's indeed a very interesting question. Like if you pump it hard enough, whether you actually can see correlated physics coming from the exciton themselves. We'll be looking at that, so we don't have any specific result on that. And the other thing is like, indeed, when you have actually exciton density quite a bit higher, they might open up, I mean, they might also increase the recombinations through an effective OJ process. Yeah, so we are looking into that, but we don't have any well-defined result here.
On behalf of the organizing committee, I'd like to thank Professor Wang one more time for his participation in our summer school and for sharing his exciting work. So thank you very much.